So, in the last class, I discussed about the three approximations for the three types of neutrino experiments with man-made sources, which lead to precision measurements of three mixing angles. And two delta m squares. It just turns out that one delta m square is measured in two different experiments and they agree with each other. So and I should mention what we measure is actually modulus of delta m square. So which mass eigenstate is lower and which mass eigenstate is higher, that these experiments cannot tell. So next issue, and the most important issue, is to measure the phase which is there in the mixing matrix. I mentioned before that because of this phase, P nu alpha nu beta is not equal to P nu alpha bar nu beta bar, where alpha is not we should mention this because if you look at the three flavor oscillation formula for survival probabilities, that third term, that imaginary part of dot dot dot, that vanishes for survival probabilities. In such a situation, you do find that nu alpha going to nu alpha is same as nu alpha bar going to nu alpha bar. But as far as oscillation probabilities are concerned, nu alpha going to nu beta is not same as the anti-neutrino oscillation probability. This is a signature of CP violation. That is, particle properties are not same as anti-particle properties. Now, for example, if I write down this probability, I find that this is equal to 1 minus 4 sum I less than j, rather, so mu. I take the general three flavor oscillation probability and I put alpha equal to mu and beta equal to mu, and you find that it reduces to this. Now, if you look at the 3x3 mixing matrix, you find that, for example, U mu2 contains delta Cp term. Similarly, U mu3 term will contain delta Cp term, etc., etc. So, there will be some terms. There are three terms here. And of these three terms, at least one of them contains delta Cp dependence. So you may argue that by measuring this nu to nu very, very precisely, you can determine this phase delta. In principle, that is a correct argument, but most people will not accept that argument that you can measure delta that way, because this probability is intrinsically, it is CP conserving, whereas this delta is the sort of source of CP violation. Therefore, this is the argument most people would make, that in order to measure delta, one should measure this oscillation probability and one should measure the corresponding anti-neutrino oscillation probability, show that they are different. That establishes that there is indeed CP violation, and having established there is CP violation, now you compare the data with your theory and determine what this delta is. So the people would insist that before you try to measure delta, you should first establish that there is CP violation, and then only you can say, I'll make an effort to measure delta. So, the sort of universally accepted method of measuring CP violation is to measure at least one oscillation probability and the corresponding anti-neutrino oscillation probability and see whether they are different or not. So, if you consider that, how many possibilities do we have? If I take alpha to be mu e, then I can have mu e to mu and mu e to mu tau. And if I take alpha to be mu, I can have and finally and the corresponding anti-neutrino probabilities. So it looks as if I have 6 choices to make this CP violation measurement. However, nature is quite unhelpful to us here, because there are essentially no sources of electron neutrinos on Earth. Reactor neutrinos are electron anti-neutrinos. So essentially the only electron neutrinos we get are from atmosphere, and for various reasons that I will explain, we prefer to have these neutrinos man-made. And in atmospheric, suppose you want to measure this in atmospheric neutrinos, there is a problem, because you have, in atmosphere, I have electron neutrinos and muon neutrinos. So an electron neutrino oscillates into a muon neutrino produces an event in my detector. But can I be sure that It came due to the oscillation of electron neutrino, because a muon neutrino without oscillating may have come and produced that event. So I have to consider a lot of details if I want to use atmospheric neutrinos. So in that sense, this is out and this is also out. Anything with nu tau in the final state is a difficult proposition, because first nu tau has to interact and produce a tau. So I need a nu tau with a very large energy, and even if that nu tau interacts and produces a tau, identifying that tau is very difficult. So this is also not suitable. And for that same reason, this is also not suitable. And we really don't have any sources of nu tau. So these two are also not suitable. So essentially, we are left with just this. We can easily get a beam of muon neutrinos from an accelerator, and if we catch those muon neutrinos oscillating into electron neutrinos, then we can measure that oscillation probability and also the corresponding anti-neutrino possibility, and look at so this is what people have concentrated on. Before we discuss this in more detail, let us in general consider delta P alpha beta. This is P mu alpha mu beta minus and this is minus 4 times I less than imaginary part of u alpha I u alpha I star u alpha j star sine 0.54 delta n squared. This is proportional to sine, not sine square. The CP violating term goes as sine. It turns out that in the quark sector also, all CP violating quantities are proportional to this combination. CP violation, of course, was first observed in the decay of K log to 2 pions, and we assume that all mesons are made of quark or anti-quark pairs. So the Kobayashi-Maskawa proposal meant that meson decays can be thought of in terms of quark decays, and if you interpret K to 2 pi decay in terms of quark decays and calculate the CP violation there, you find that that CP violation also is proportional to this quantity. And in 1983, a Swedish physicist called Cecilia Jarlskog, she proved an important theorem. She showed that this imaginary part of is some mod J. It is independent, or rather I should write it a bit more carefully, minus 1 power something times J. The power of this minus sign depends on this I, J, alpha, beta, etc. I don't remember the exact dependence, but J is independent of alpha, beta, I, and J. If you count, you find that there are actually 9 possibilities here. There are 3 ways of choosing alpha and beta and 3 ways of choosing I and J. So there are 9 possibilities. And if you take the PMNS matrix and calculate all these 9 quantities, you find that they all have the same magnitude. They only differ by a sign, and that sign depends on what this alpha, beta, I and J are. And in fact, one can show that this J is cos theta 1, 3. For the parameterization that we chose, this is cos theta 1, 3, sin 2 theta 1, 2, sin 2 theta 1, 3, sin 2 theta 2, 3, So you notice that if delta is 0 or pi, there is no CP violation. And if any of the mixing angles are 0 or pi by 2, then also there is no CP violation. And there is a further part of this theorem which shows that CP violation is 0 if any 2 masses are the same. This is true actually both in quark sector as well as in neutrino sector. And in quark sector actually all these theta 1 to theta 1, 3, theta 2, 3, they are all quite small. So the amount of CP violation in quark sector is quite small. But luckily for us, in neutrino sector, sin 2 theta 2, 3 is close to 1 and sin 2 theta 1, 2 is like 0.85. Only sin 2 theta 1, 3 is a bit small, but not too small. It's about 0.3. So the magnitude of CP violation, the intrinsic magnitude of CP violation in neutrino sector actually essentially depends on what delta is. So if I measure the difference of those 2 probabilities, I know it is proportional to J, and I know precisely what this P factor is. So I can determine sine delta. So looks like a nice clean program which can be implemented in a very straightforward way. But here nature has sort of thrown a googly, and well, depend. It is useful from one point of view, but of course it makes the measurement of CP violation very difficult. So let us look at that. That is to do with matter effects. The matter effects were first considered by an American physicist called Wolfenstein. And he was thinking of propagation of neutrinos through dense matter. I hope all of you have studied this topic in your study of electrodynamics. When you have a photon passing through a dielectric, especially a transparent material, it keeps getting scattered by the electrons in that material. But if it gets scattered, it's not going off in an arbitrary direction. It is actually going in forward direction only. But this scattering of the photon with electrons, it alters the propagation of the photon through this material, and that we characterize as refractive index. And Wolfenstein felt something similar should happen when you have a neutrino going through matter. So neutrino in principle has weak interaction with the terms with the particles in the matter, protons, neutrons, and electrons. And the scattering amplitudes in the forward direction, they will all add up, so that they will all add up coherently, so that even though the interaction between neutrino and a particle of matter is very, very weak, because you are adding up this Avogadro number of atoms, effect of Avogadro number of particles coherently, that can be a substantial and visible effect. And he gave a formalism for it. And based on that formalism, later Mikhail and Smirnov proposed a solution to solar neutrino problem. We will consider those details later. But what I want to emphasize here is that matter effects are useful in one sense, and they are a headache in a different sense. So let me discuss that. let me discuss the headache part. So I have a neutrino traveling through matter. So I have neutrino with some matter particle. I call that matter particle M. And this is elastic scattering. So matter effect arises due to this elastic scattering of a neutrino scattering on a matter particle. It can be electron, it can be proton, or it can be neutron. And corresponding to this, we have some matter tone. I call that A. But instead of neutrino, suppose I have an anti-neutrino. So the scattering which gives rise to matter effect is scattering of anti-neutrino of a matter particle going into anti-neutrino of a matter particle. And you will see later that we parameterize this scattering in the form of a potential, and you all know that if I call the matter potential V, then the matter antimatter potential is minus V. So this leads to a matter term minus A. Now you see the problem that I face. I'm shooting a new beam from here, and this is the Earth, and here is my detector. A is some term which is parameterizing the matter effect. What it is, we'll see later. But what I am claiming is this interaction between neutrino and matter particle, I parameterize it in the form of a potential. And for matter-matter interaction potential, if I call it V, then antimatter-matter potential is minus V. So if I parameterize the matter term for this scattering as A, the parameterization of matter term for the anti-neutrino scattering is minus A. So this is the important point I am making, that scattering of neutrino of matter particles, that is different compared to scattering of anti-neutrino with matter particles. So this neutrino is going through earth matter and entering my detector, and I measure the oscillation probability. But I just claimed that the passage of neutrino through matter modifies the propagation properties, therefore it modifies oscillation properties. And if I replace these neutrinos by mu bar, then that also is modified by matter terms, but that modification is different compared to the modification of mu that I have for mu. Now, mind you, these interactions are not CP violating. These are very simple scattering matrix elements. They are not CP violating at all. However, since this interaction and this interaction are different, their effect on neutrino propagation and anti-neutrino propagation are different. Therefore, even if there is no CP violation in neutrino oscillations, I will get a difference in nu mu to nu e and nu mu bar to nu e bar because of the matter effects. Do you appreciate this point? This is the crucial point which makes life very difficult in doing this experiment.
Matter is breaking the symmetry between matter and antimatter.
Yeah. No, for example, imagine, suppose I get a tube of antimatter and install it along the beam path. Then there will be no problem because CP invariance, then not CP invariance, actually CPT invariance tells me that this interaction and this interaction are exactly the same. Then this becomes plus A again. Matter potential, antimatter potential are the same. So this quote fake CP violation is coming because I am not able to replicate the antimatter part of the scenario properly. I mean, the earth consists of matter. So the matter term in one case is matter potential, in another case is matter antimatter potential. And even though this interaction and this interaction, they are not CP violating, but the initial conditions, so to speak, are CP violating. Therefore, the results I get in nu mu to nu e and nu mu bar to nu e bar, they will be different even if the neutrino oscillations are CP conserved. And if neutrino oscillations are intrinsically CP violating, then I have the job of disentangling the intrinsic CP violation from this fake CP violation. So I mean, for example, you want to say that in the case of photons, there are no antiphotons, so things are a bit this one, but I'm measuring, I do an experiment with particles and I do an experiment with antiparticles. And I ask, are the results same? If the results are same, then I say there is CP conservation. If the results are different, I say there is CP violation. I define whatever in the case of quarks, it is the decay rates. And here in the case of neutrinos, it is the oscillation probability. So, starting point, nu mu, endpoint nu e. That is the experiment with particles. Starting point nu mu bar, endpoint nu e bar. That is the experiment with antiparticles. Now, if in between the starting point and the end point, if I have only vacuum, then all I need to worry about is starting point nu mu, measuring nu e, and starting point nu mu bar, measuring nu e bar. End of story. But there is typically, these are long baseline experiments with hundreds of kilometers distance between the source and the detector, which means the neutrino necessarily goes through earth matter. Earth matter is always matter, there is no antimatter. So nu mu, as it is converting to nu e, is constantly interacting with this earth matter. Similarly, nu mu bar, as it is converting into nu e bar, is constantly interacting with this earth matter. Now, if I want to have, in order to look for intrinsic CP violation, I should have, in the first case, nu mu interacting with earth matter on its way to conversion to nu e. I must have nu mu bar interacting with antimatter on its way to conversion to nu e bar. I don't have antimatter, I have matter. And I know matter-matter interaction is different from antimatter-matter interaction. So, the way the nu mu to nu e probability will change is different from the way nu mu bar to nu e bar probability will change. So that is what I mean. The initial conditions in the two cases are different. In the propagation of neutrinos, I see neutrinos see matter. But in order to check for intrinsic CP violation, I should replace everything, starting point, end point, and all intermediate points by particles, by antiparticles. I'm not able to do that. I've replaced nu mu by nu mu bar, nu e by nu e bar, but earth matter is remaining earth matter. So, because of this, the two setups are not exact CP copies of each other, and because of which a fake CP violation comes in the oscillation probabilities. Even if intrinsic CP violation is 0. And if intrinsic CP violation is non-zero, I have a job of disentangling what is intrinsic CP violation and what is fake CP violation. So, the job of measuring the phase delta is much more complicated than simply measuring nu mu to nu e, nu mu bar to nu e bar, and see whether they are different or not. So, this is the problem that we are facing, and in order to solve this problem,
experimentally we can have a long beam pipe with a vacuum.
yeah, but that is too expensive. Hey, there are cheaper options available, let me put it that way. So, in principle you are right, but there is a cheaper option available, and that cheaper option actually has a payoff. So now let's talk about the positive aspects of matter effects. In discussing the neutrino mass eigenstates, I said there is mu1 with mass m1, mu2 with mass m2, and mu3 with mass m3. And we said we want to solve both solar neutrino problem and atmospheric neutrino problem using oscillations. And the delta m square needed to solve solar neutrino problem and the delta m square needed to solve atmospheric neutrino problem, they differ from each other by at least one order of magnitude, which immediately means that of the three mass square differences, two are large, magnitude wise, two are large and one is small. And then I said, without loss of generality, the two masses which are closer together, I call them 1 and 2, and the one which is farther apart, I call 3. So if I try to draw a picture, I can have a pattern like this, or I can have a pattern like this. Two close, third one far away. Question is, the third one above or third one below? But now, of the two ones which are close, is the lower one M1, upper one M2, or the other way? That also is a confusion. So in that sense, there are actually four possibilities. That is, delta m square to 1 positive or negative, delta m square to 1 positive or negative. And as far as vacuum oscillations, especially the effective two-flavor approximations that we have made, from those all these four solutions are equally good. The effective two-flavor oscillations, they won't tell you about the sign of delta m square. However, and this we will see in the next class, the matter effect when we start discussing the details of the matter effect, we find that the modification takes the form of some kind of interference. So the matter term, which I called A for matter and minus A for A for neutrinos and minus A for antineutrinos, that interferes with delta m square. So if delta m square is positive, then that interference term will have one sign, and if delta m square is negative, then the interference term will have a different sign. So if you are able to measure the modification, the change in the probability induced by matter effects, you can tell whether delta m square is positive or negative, and similarly both here and here. And let me just give you the present knowledge. The which we equated to delta m squared to 1 to be positive. So, of the two possibilities, delta m squared to 1 positive or negative, solar neutrino data is ruling out the negative sign and has fixed it to be positive. But as of now, we don't know whether delta m square 31 is positive or negative. So, of these two patterns, I have 1, 2, 3, and here delta m square 31 is positive. And here delta m square 31 is negative. But whether this pattern is correct or this pattern is correct, I have no idea. So, the ideal situation is so you take an experiment and measure the sign of delta m square 31 in it, where the effect of deltas, that CP violation delta, is negligible. And once you know this, then life becomes much simpler. If I know whether delta m squared is positive or negative, I know precisely how neutrino probability changes, how anti-neutrino probability changes due to matter effect, and then I measure those and ask the difference between the two. Can I explain it purely based on matter effect, or do I need to include CP violation also? So that's how the chain of logic goes. and then ask if delta mu e in long baseline experiments is purely due to matrix effects or carries effect of delta also. And this is where INO plays an important role, because in the case of atmospheric neutrinos, you have neutrinos coming from all directions. So the distance between neutrino source and the detector, for neutrinos coming from above, it's about 10 kilometers, but for neutrinos coming from below, it is 13,000 kilometers. So you have L varying over this huge range from 10 kilometers to 13,000 kilometers, and also energy varying from around 1 GeV up to some 20 GeV or so, beyond which the flux is too small. So since you are adding up data over this huge range of L and E, you find that the terms where delta Cp plays a role, those terms tend to cancel out, and the muon neutrino survival probability, or the muon neutrino rate, is essentially insensitive to delta Cp, but is a fairly strong function of the matter effect. So the hope is INO can determine the matter, measure the matter effects, and can tell whether delta m square 31 is positive or negative. And if you have that, then the long baseline experiments, they measure P nu mu to nu e, P nu mu bar to nu e bar, and you take the difference between the two, and you ask, is the difference, can I explain the difference purely in terms of the matter effects, or do I need to include the intrinsic Cp violation also? So that is how the sort of the chain of logic is proceeding. There was some hope that long baseline experiments by themselves could actually do the job, but from their data, which was taken over the last 4 years, we find that they are not able to. So there is another proposal called DOOM, where it's also a long baseline experiment, but it is being designed in such a way that sort of you learn from the current failures, so to speak, so that in the case of DOOM, they can actually measure both the sign of delta m square 31 and delta Cp both in one shot. It can be done, but it needs some special conditions, and people realize what those special conditions are and are designing DOOM according to that. We'll discuss that. Basically, you need a higher energy. the neutrino beam energy should be about 3 to 4 GeV.
This sign of delta M square it comes into, it plays any role only if there is matter. Without matter effect,
Yeah, without matter effect, the sign does not play much role, at least as far as oscillations are concerned.
or something else.
For example, an important subtopic in neutrino physics is neutrinoless double beta decay, which I'm not going to discuss in this course. And there it actually makes a difference, in fact a very important difference. See, we know that the mixing between the third state and electron neutrino, the UE3 element, that is sine theta 13, and that's 0.15. That mixing is very small, which means that nu1 and nu2, they have large overlap with electron neutrino. And if this is true, then these high mass particles have large overlap with electron neutrino, and that is very favorable for neutrinoless double beta decay. Whereas if this is true, then it is the lower mass particles which have large overlap with electron neutrino, and that is not so favorable for neutrinoless double beta decay. But I mean, people actually hoped that neutrinoless double beta decay can actually tell us whether this is true or this is true. But the effective mass which appears in neutrinoless double beta decay, there is only an upper limit, and that upper limit is going down and down, so that now it is felt that one cannot really expect much from there. And another place, of course, is in model building, in building a model of neutrino mass. So if you know a priori whether this is true or this is true, you put that information in building your model. So from the model building point of view, it will be very helpful. Okay, so I will stop now, and from the next class, I will start the formal discussion of matter effects.